Alright, so as I said before, I was going to do the Basel series two different ways. And then the third thing I'm going to do for my series is the Gaussian integral, which is the area under the bell curve. But the other way I was talking about, the less intuitive way. So again, the Basel series is the sum of n equals 1 to infinity of 1 over n squared. And it looks like this, right? So if we actually start listing in terms, it goes 1 plus 1/4 plus 1/9 plus etc. Actually, I don't like that. Let me just... Yeah. So now let's take a... Because, okay, this is not intuitive, right? So what I'm going to do next is going to be weird. But let's take a look at sine of x. So if you take in Calc 2, you will know that the sine of x actually has a Taylor series that looks like this. So remember, sine of x is an odd function. So it looks like this. It's going to be -1 to the n, and then it's going to be x to the 2n plus 1, and then it's going to be all over 2n plus 1 factorial. So that's what sine of x looks like. And if you start listing out terms, the first term is x, you plug in 0. Then it's going to be minus x cubed over... I'm just going to write 3 factorial instead of 6. Then it's going to be plus x to the 5th over 5 factorial, and so on. So now if we replace all these other terms, let's just call that some variable t for tail, then we can just say sine of x is going to be equal to the tail minus x cubed over 3 factorial. Let's say we're grouping all the terms together that's not cubic. So now that we have that, now, again, this is not intuitive. So we can write like an infinite polynomial to describe sine of x. So what happens if we try to factor that infinite polynomial? So it has a 0 at 0, and then it has a 0 at pi, and it has a 0 at negative pi, and it has a 0 at 2 pi, and it has a 0 at a negative 2 pi. So now, if we look closely, this is actually a difference of squares. So there's multiple differences of squares. That means that we can combine them, where we can treat this as a difference of squares. So we can really write this as x. This would be 1 minus x squared over pi squared times 1 minus x squared over 4 pi squared, and so on. So now we have this infinite polynomial. So now if we just try to distribute against this infinite polynomial, we're going to have a linear term and then a cubic term, right? So now if we do the same thing we did before, we have this tail, and then we have all the cubic terms. But notice when we distribute the x to the x squared terms, that the cubic terms look like this. So we factor out an x cubed over pi squared. Then what we're left is just a 1 plus 1/4 plus 1/9, and so on. It actually keeps going. And notice that this is the same thing as this. So we can actually replace that with that. We can replace that. So we can say that sine of x is really just a tail, the tail terms, minus x cubed over pi squared times the sum from n equals 1 to infinity of 1 over n squared. But sine of x is also equal to this. So now we set them equal to each other. So we have a tail minus x cubed over pi squared, the sum from n equals 1 to infinity of 1 over n squared equals a tail minus x cubed over 6, which is prefactorial. Now we can cancel the tail on both sides, and then the negative sign on both sides. So this becomes a plus, that becomes a plus. And now what we have is here, and then we could divide out this x cubed term too, actually. And then now all we got to do, so now we have 1 over pi squared, the sum n equals 1 to infinity of 1 over n squared is going to be equal to 1 over 6. Now all we got to do is just multiply both sides by pi squared. And now we're left with the sum from n equals 1 to infinity of 1 over n squared. It's just equal to pi squared over 6. And that's what we got with the... hold up, I don't like how that looks. And that's what we got with the integral method. But this one is way quicker, but it's less intuitive. We have concepts of affinity. You guys know about the Taylor series for sine of x. Well, I guess more accurately, mclaurin series. You have to know about the you have to factor an infinite polynomial. This is actually known as a weierstrass product. Well, that wasn't a thing at the time, because I know this kind of looks trivial now that I'm doing it, but this was a new concept when Euler did it. So yeah, he invented, and then later on it was more perfected and generalized to all functions, and that was known as a weierstrass product. But yeah, there we go. Nice, simple, and sweet. So that's another method of proving it.